Thanks, Valerie. Thanks for the kind introduction, and I'm happy to be here today. And I want to tell you about, it's not one paper, it's sort of a series of recent papers on sustaining delay of gratification and the cognitive and neural mechanisms of that. And I'll even get into, in the future directions, I'll give you a taste of some of our work on mental health as well. But I like to start out with an example of the kind of behavior that I'm interested in explaining. So this is a dilemma that I often face. I would like to look like the guy on the right. I don't, if you haven't noticed. But I also have a very strong sweet tooth. And these are two goals that I can't simultaneously fulfill, right? If I want to look like the guy on the right, I have to give up eating cake for dessert. Now, from the outset, when you have these conflicting goals, when you have these two options, there's nothing irrational or inconsistent about saying, well, saying something that our evolutionary ancestors might think is crazy, which is, I'm going to forgo this packet packed with calories and diet in order to look like the guy on the right. Similarly, there's nothing irrational or inconsistent about resolving the dilemma the other way, saying, you know what, I'm never going to look like the guy on the right, and I enjoy a slice of chocolate cake. I'm going to live for the moment, and I'm going to resolve the dilemma the other way. However, there is something puzzling about the following pattern of behavior, which I often see myself engage in, and I'm sure many of you engage in, which is we say initially, I want to look like the guy on the right, so I'm going to start a diet. And I persist in the pursuit of that delayed reward. I persist in the diet and the pursuit of that delayed reward of looking like this guy for months or days or hours, and then a piece of chocolate cake comes around and I go, you know what, sorry about that, I got that wrong. I don't scratch that earlier choice. I'm going to have the chocolate cake. And so this is the behavior that I want to try and explain, which is choosing to pursue a delayed goal, a goal that's in the future, going down that road for a little while, and then abandoning that goal. That's the reversal. That's the kind of behavior that I'd like to explain. And the reason I'm interested in this behavior is that it's ubiquitous. Anyone who's ever made a New Year's resolution has probably engaged in some variant of this. And there's lots of examples: dieting, quitting smoking, addictions, studying, where people initially choose to pursue a delayed goal and then abandon that pursuit. So much so that one view is that one simple explanation for this kind of behavior would just be people are really bad at persistence. However, I don't think that's the case, because I think I can point to lots of other situations where people are remarkably persistent. Here's my favorite example. The folks in the line at the Apple store. You don't have, there's no one who's like midway down this line who, after waiting for 3 days for the new iPhone, says, you know what, I just can't do it anymore, and leaves the line without getting their iPhone. And so what I want to try and understand is what differentiates those situations where people have trouble persisting in the pursuit of delayed goals from those situations where people seem to be remarkably good at persisting towards delayed goals. I'm going to try to convince you that a key component that differentiates those situations is the nature of the temporal uncertainty of the delayed reward, right? What's different between the dieting and the smoking, stopping smoking situations and in the line at the Apple store situation is what's the nature of the uncertainty about the thing that you're waiting for. Hopefully by the end I'll have convinced you of that view, I think this sheds some light on why we have trouble with persistence in some situations but not others. Now, before I get to the outline, just one sort of philosophical point, which is I think once we get to the end and I say, well, look, there are some situations where people have no trouble with persistence and it's easy, there is a tendency on the part of some people in different fields to say, that's great, but now you're no longer studying persistence or self-control, right? In other words, there's one view that self-control is simply a subset of effortful control, right? So we have kinds of effortful control, we have kinds of cognitive control, and what self-control is just a subset of applying effortful control to situations where you're pursuing long-term goals. I take a fundamentally different view of how to define that term, self-control, which suggests that only a component of behavior that is self-control behavior is effortful control. And I take inspiration from my colleague Angela Duckworth, who in writing with James Gross says, actually, the self-control that seems to be most effective often is that part that's in the white part over here. It's the part where people are being self-controlled without having to engage in effortful control. So it's within that spirit that I think this, this distinction between situations where people are persistent and where it's hard for people to persist and situations where it's easy for people to persist is an important is still within the domain of studying self-control and delay of gratification. So here's the outline. I'm first going to give you some background on the theory and the computational formalism for this set of investigations. I'm then going to go in to some of the behavioral evidence for this, for the importance of temporal uncertainty in people's ability to sustain persistence towards delayed rewards. And then at the end, I'm going to add some neural evidence for pieces of our story as well about the importance of temporal uncertainty. And I should say at the outset that most everything I'm going to tell you about is work in collaboration with Joe McGuire. I usually, my sort of standing comment about Joe is he's fantastic, you should hire him, but you can't hire him anymore, he just took a job. So, but he's still fantastic and really deserves a lot of the credit for the work that I'm going to tell you about. So first, theory and computational formalism. So where we started on this was taking some inspiration from the very well-known set of experiments done by Walter Mischel on delay of gratification. I'm sure this is familiar to most of you in the room, but this is a set of experiments where Walter and his colleagues put children in the situation where they come into an experimental paradigm. He puts before them two rewards, often one marshmallow and two marshmallows, or one marshmallow and three marshmallows. He says, which would you prefer to have? They say, I want the bigger pile of marshmallows. And he goes, great, if you want the bigger pile of marshmallows, I'm going to go out of the room for a while. But if you wait until I come back, you can have the bigger pile of marshmallows. If at any point in time you're sick of waiting, though, you can ring the bell and bring me back in. And what he sees is that there's a large group of children who engage in this kind of reversal behavior that I started the talk with. They say, I want the bigger pile of marshmallows. They wait for a little bit of time, and then they cancel that choice halfway through and ring the bell and say, give me the one marshmallow. And I think we drew our inspiration from this task, in part because I think part of the reason that it's so famous is that it captures these dilemmas that people have in everyday life. And I think it also captures the temporal structure of the dilemmas that we face in everyday life, right? So in the delay of gratification paradigm, you have one marshmallow that's always available immediately. You have three marshmallows that's available at some point in time in the future, but you don't know when in the future you're going to get them, right? You know that at some point in time in the future, the experimenter's coming back, but you don't know when that is. And I would argue that that's a decent description of the temporal structure of my dilemma, right? If I'm on a diet, I know that if I persist on that long enough, I'll likely lose some weight. Right? If I persist on it long enough, I'll lose some weight. I don't know exactly when that will be. However, in the world that we live in, chocolate cake is, we can is almost always immediately available, right? It's not always right in front of me, but it's easily obtainable. And so the first question we started with is in decisions of this form, where there's this temporal description of these decisions, what should people do? Before I get to that, though, let me just hammer home the notion that in the original delay of gratification paradigms, there's uncertainty. I think often the way these experiments are described in the popular press, the uncertainty is elided, right? So, but here's the initial description. These are the exact instructions given to the children. I have to go out of the room for a while, but sometimes I'm gone a long time, and if you want to bring me back, you can. So all the child knows is for a while. Just 5 years later, this was described by George Ainsley in the following manner. Each subject was told he could have a food he preferred if he waited for 15 minutes, or an unpreferred food immediately whenever he wanted to stop waiting. So already what you're seeing there is, Ainsley's description of the experiment is the description. This is a classic theory of mind error. Ainsley's description of the experiment is the description of the experiment that you would give from the perspective of someone who's read the methods section and knows that the child only has 15 minutes to wait. But from the child's perspective, the information that the child has access to is that there's an uncertain point in time at which they'll get the larger reward. So when you're faced with these dilemmas of you have an immediately available reward and a delayed reward that's greater, but the arrival time of that delayed reward is uncertain, what should you do in those situations? Turns out that what you should do depends critically on your beliefs about the possible times that the delayed reward might arrive. Right? And that the behavior actually, the dynamics of the behavior depends critically on that, the uncertainty over when the delayed reward should arrive. In other words, in order to, and how is that? So I'll give you two examples. First, let's imagine that your belief about the possible times that the delayed reward could arrive could be described by this probability distribution. This is just like saying, look, it's most likely that the experimenter will come back in 3 minutes. However, that's 3 minutes plus or minus 1 minute. It could be 4 minutes, could be 2 minutes. This is most likely, but the probability that the experimenter comes back at other times drops off in a Gaussian manner. Now what I'm going to do is just walk you through how if you were making completely accurate predictions, starting with this belief, if you were completely accurately updating your belief, how that belief would change as you waited through time but did not receive the reward. So all we're going to do is, as you wait through time, that rules out all the things in the earlier time points. That means that you should update your prediction about when the reward occurs based on what's left of that distribution. And what I'm going to plot is you, in a dark line as you move through time. The gold bar is your prediction about where the reward will occur now as you move through time. And on the right here is the distance between those two as you move through time. So here's what that looks like. As you move through time, ruling out the early time points at which the delayed reward might occur, your prediction about when the delayed reward occurs is going to be pushed back in time. However, if you start out with Gaussian beliefs, the distance between those two is always decreasing. So the amount of time that you think you have left to wait is always decreasing. So if you started with this belief about the possible times that the reward would occur, if it made sense to initially start waiting, it would never make sense to stop waiting once you've started waiting, because the delayed reward is only getting closer to you, and if it's discounted by its delay, it's only getting more valuable. However, a different condition obtains if you start with a different form of beliefs about when the delayed reward might occur. So in this case, this is showing what the probability distribution would look like if you had heavy-tailed beliefs about when the reward might occur. To say this in words, it's more likely that the reward could occur early rather than late. However, very late, very delayed points in time are more probable, right? So there's a long, heavy tail here suggesting that very delayed points in time are possible. It's most likely that it's going to come soon, but very delayed times are possible. This is the distribution that you would get if there was some time constant that determined when the reward occurred, but you just don't know what time constant that is, right? So it could be a fast process or it could be a slow process that generates the reward. Both of those are possible, and at the outset you don't know which process is generating the reward. Now something very different happens as you move through time, ruling out the early points in time. Something very different happens to your predictions about when the delayed reward will occur, and to your predictions about how much time you have left before the delayed reward arrives. Now what you see is that as you move through time, ruling out those early points in time, and you're just, updating your predictions accurately, both the predicted arrival time of the reward moves farther in the future, and the distance between you and the arrival time of that delayed reward is growing as a function of the time that you've waited. The intuition here is that if there's a mixture of possible processes, it could come fast, it could come slow. If you've waited for a time and it hasn't happened, that makes the fast process less likely and the slow process more likely. And in this case, that's true to such a degree that your prediction about how much time you have left waiting is more than when you initially started waiting. And in this kind of situation, it would now be completely rational for you to start waiting for a delayed reward and then stop at some point because your prediction about how much time you have until it comes has gone beyond where it was when you initially started waiting. So this is potentially a rational explanation for the kinds of behavior I started out the talk with. Initially pursuing a delayed reward, saying I'm going to wait for a delayed reward, but then abandoning that pursuit before you receive it. So, yeah. Yeah.
So your assumptions about how far the tail goes out changes as well, or does the assumption about how far the tail goes out stay the same, but you're just at a different point?
You're just at a different point. Your assumptions about how far the tail goes out don't. In this, we could add that on top of this, but that's not a feature of what I'm saying here. Okay. So now you might ask, great math, but what do heavy-tailed distributions have to have anything to do with kids waiting for marshmallows or any other real-world behavior? Well, we know that there's lots of things in the real world that are distributed in a heavy-tailed manner, and it's interesting to look at those things that are distributed in a heavy-tailed manner because I think it gives you some intuition about where this kind of distribution is acting. So my favorite example is email replies. So for the students in the room, if you send an email to a very famous professor, you've probably had this experience. There's a good probability that they're going to email you back right away. There's also a good probability that they're not going to email you back for a very long time. That very long time could be never. It could also be a very long time. There's a famous professor I emailed who emailed me back, who responded 4 years later. So, and I think our feelings, right? You send an email, you don't get a response. Your feeling about, your expectancy of a response declines. Your expected, return time declines as a function of how long you've been waiting for a response. Also, wait times on hold, distributed in a heavy-tailed manner, and I think this is another situation where perhaps this gives you some intuition about what kinds of situations in the real world have this feature. We probably all have the strong intuition that the longer you wait on hold, the more frustrated you are, and the longer you think it's going to be. Right? If I call a company up and they put me on hold, for the first 5 or 10 seconds, I have the phone here at my ear. After that, I put it on, I put it on speaker and I start answering my email. And there's a theoretical argument from a number of different sources suggesting that if you don't know, so one reason people might have a heavy-tailed belief in their heads is because they have lots of experience with the relevant distribution, and they've learned, perhaps not even consciously, that it's a heavy-tailed distribution. Another reason is that it might just be, this sort of thing might be built in, because if you don't know anything about a distribution, there's strong theoretical arguments that the prior of ignorance in this case would be a heavy-tailed distribution. And that the argument that that's the right prior of ignorance is just that you don't know the time constant of the process that's going to deliver the delayed reward, and so you average over all of those time constants, and what you get is a heavy-tailed distribution. Now, what this sets up is a couple of ways in which people in the real world could be miscalibrated, right? One way in which people could be miscalibrated is that the actual distribution is Gaussian, but what they have in their head is this is a heavy-tailed case. And this might be what's going on in the case of the kids in the delay of gratification experiment. We know that the experimenter is going to come back at 15 minutes, but what they have in their head is not that the experimenter is coming back in 15 minutes, and their behavior is being driven by what's in their head, not what's in the real world. But you could also go the other way, and which is the real world could be distributed in a heavy-tailed manner, but you could believe that it's Gaussian, and this might be part of what's going on when people are chasing sunk costs, right? That really what they should be doing is they've waited long enough, they should abandon the delayed reward, but they have this feeling that it's just around the corner, and that's driving them to chase sunk costs. So what the theory, these theoretical ideas show is that temporal beliefs can offer a rationale either to persist if your beliefs are Gaussian or uniform, or to quit when you're delaying gratification, when you're waiting for delayed rewards. And so now the question is, does this, is there any behavioral evidence that this is relevant to real-world delay of gratification? Is there any behavioral evidence for that? So the first thing you can ask is whether people's expectation about the time remaining in any given dilemma increases as a function of the time waited. So remember that the signature of Gaussian beliefs is that your expectation about the time you have left to wait decreases as a function of how much time you've waited. The signature of heavy-tailed beliefs is that your expectation about how much time you have left increases as a function of how much time you've waited. And so this gives us one way of testing which of these holds in different scenarios that people might face. And we're indebted here to, we're basically borrowing the methodology of Tom Griffiths and Josh Tenenbaum in eliciting these predictions and using those predictions to infer what someone's beliefs were, or what someone's beliefs are about the distribution, right? So we're using this rather than trying to elicit a full probability distribution from someone, which might be possible, but is certainly hairy methodologically, and this I think is an easier entree into getting a sense of what people's beliefs might be. So first, let me just show you some data to suggest that people do sensible things when we ask them to make these predictions. On the left, what we asked people to predict was how much time is left in a movie. Movie times are normally distributed around 2 hours or so. So if people are making these predictions sensibly, this is just a manipulation check. If people are making these predictions sensibly, and they know, that movie times are distributed in a normal manner, in a normal distribution, then what we should see is that their prediction about how much time is left in a movie is a decreasing function of how much time we tell them has already expired, right? Like the movie's already been an hour and a half, how much time do you think is left? And what we see is very sensibly declining predictions about time left as a function of time waited in the movie case. So now we can take this method and apply it to other situations that we might be interested in to see what people are thinking about in those situations. So in the first case, let's just take the standard delay of gratification scenario. Let's describe what that experiment looks like and then ask people, the kid has been waiting for 2 minutes. How long do you think it's going to be until the experimenter comes back? The kid has been waiting for 10 minutes. How long do you think it's going to be until the experimenter comes back? And there we see something quite different from the movie scenario and consistent with people coming to this situation with heavy-tailed expectations, which is that people's prediction about how much time the kid waiting has left is an increasing function of how much time they've waited. We then extended this to a number of other scenarios that are commonly thought to involve self-control. So we tell people you've started a diet, you've been on that diet for 5 days, 15 days, 30 days, you haven't seen any changes. How long do you think it's going to be until you reach your goal? And we see that their predictions about how much time it's going to be until they reach their goal are an increasing function of how much time they've waited without seeing any effects of the diet. We do a similar thing with training, with running to reach a goal. How many days have you been training without reaching your goal of running this distance but in this amount of time? And what's your prediction about how long it's going to take until you reach your goal of running this distance in this amount of time? The longer it's been without you reaching your goal, the longer you think it's going to be from the point in time at which you're at until you reach your goal. Similar with studying to do better on a test or to do better on the LSAT. Similar with practicing the piano to learn a piano piece without any errors. In all of these cases, what we see is that the more time has elapsed without people reaching their delayed goal, the longer they believe it's going to be from where they are at the moment until they reach their delayed goal. Yeah?
So are these simulated data where you're just asking people how long they think it'll take, or are you actually behaviorally observing this?
These are, good question. These are survey data. We've done it several different ways. These data are, each person just gets one question. So we say, you've been on a diet for 15 days without seeing any results. How long do you think it's going to be until you reach your delayed goal? But they're not necessarily dieting. They're just saying, if you were in this situation, what would your prediction be? We can also do it within subject. It works within subject, between subject. What actually gives in the survey case, what gives the strongest results, the strongest increasing linear trend, is to start out asking the 5-day question and then the 10-day question and then the 15-day question, in the way that you would in sort of natural progression of time. But anyway, we ask the survey, we get these results. I agree that it would be great to get real-world predictions from people who are on diets or from people who are, in the midst of a quit attempt. How long do you think it's going to be until the cravings for cigarettes go away? And we'd love to get that data. We don't have it. But this, I think, the point here is just to establish the plausibility that heavy-tailed expectations may be acting in these situations.
But do you suspect that it would be the same if you're actually in the moment? You can imagine situations like the ones that you've talked about where people are motivated to think change is just around the corner. So I've been waiting for 2 months to get a decision on a manuscript I sent in. I think it's, anytime this week. It's not like all of a sudden I'm thinking it's going to take a year or something like that.
Yeah, well, I mean, the manuscript case, I don't even know, if we were to do this survey prediction exercise as opposed to in the moment, what people would say. It's quite possible that there's other, like the movie scenario, there are other scenarios where people are waiting where they don't have heavy-tailed expectations. But the question of whether things could be different in the moment, I would grant that you could that you could see differences in the moment, that people could be, that this could be enhanced, or that based on emotional state, this could be enhanced. This feature of increasing predictions as a function of increasing time could be enhanced or decremented based on emotional state.
Yeah, even waiting on hold, it seems like everybody would be hanging up if this was their expectation. I'm sure a lot of people do hang up.
Yeah, I've certainly hung up.
But it also feels like I guess it's like a sunk cost thing. The longer that you've stuck with it, the more likely you might be to think somebody's going to get on the phone within the next minute, and you keep thinking that for 30 minutes.
I think the important point, the important point that's buried, that's within your comment, that is sort of the point that I want to make, is that people's behavior will be determined by what expectations they bring to the situation. So if their expectations are that it's right around the corner, that would lead them to be persistent. Whereas if if they don't have that strong expectation that it's coming right around the corner, that they wouldn't be persistent.
Joe, if I could pursue for a minute the difference between no experience and experience.
Mm-hmm.
In your Gaussian, you know the mean, and in your heavy-tailed, you don't. That seems to me a fundamental difference. So when you ask people on surveys, how long do you think it will take someone, right, or you, and if you have experience studying or dieting or running, you've got a mean, and you don't have, I don't think, how often is the distribution where you have experience heavy-tailed versus the survey where you're guessing about some person, and that's more likely to be heavy-tailed because you have no experience in the survey. It's a sort of generic question.
Well, so I think there's 2 points there. One is that if you don't, this could be operating in situations where you don't have experience. And I think there's lots of situations where we don't have experience. So I think it's going to be relevant in those situations where we don't have experience. No, yeah. So then the question is, are there any cases where we do have experience where this is relevant? And perhaps, so I can give you an experimental case. That's actually where I'm going next, which I give people experience with 2 different distributions, and I show that they behave according to those 2 distributions. I would argue that the hold case, and so the hold case and the email case are 2 cases where the actual distribution out in the wild is heavy-tailed, and those are things that we have experience with. So I think there are certainly, and then the argument is going to be, and this I don't have data on, is, in the dieting case, are success times on diets heavy-tailed or Gaussian? My intuition would be that they're heavy-tailed, but I don't have the data to back that up. That's something that we could look at.
So my concern is that in the example you gave initially, which seems to concern you, dieting, and in many other examples, it's repeated, and people do have experiences. And the question is, in those situations, is it really heavy-tailed? If you're on hold, and by the way, the difference between the dieting and the hold situation is control, which also is your focus. So in the hold situation, you have no control. You're just on hold, and you're sitting there with the damn receiver in your ear, or you put it down, or whatever. But in dieting, you have control, and you must have a lot of experience in terms of your own control of what the mean of distribution is and what it looks like. And that's my concern.
Yeah. So I think I think there's a lot of work to be done on learning and how people respond. From the point in time at which you start out, where you might have no information, to the point in time at which you've had lots of information. How is people's behavior changing? I'll give you some data on that here, and then maybe we can come back to it. It's not dieting data. I'd love to have the data on dieting. It's a controlled laboratory experiment. But let me. So let me get to that. So the next question we have is, can people learn the statistics of the environment and adjust persistence accordingly? So can we take people from a situation where they don't have any knowledge of the statistics, we drop them into a Gaussian environment or a heavy-tailed environment, and do they adjust their persistence behavior accordingly? Here's the task that we're doing. To make things simple and to make the point that your expectations about the delayed outcome can drive abandoning that outcome, we've simplified it. There's only one outcome here. It's the delayed outcome. In this experiment, subjects are given tokens. At the beginning of the experiment, or sorry, at the beginning of a trial, a token is not worth any money. At some point in time, that token matures and it's worth 30 cents, and you can make money by selling that token back to the experimenter. You can also sell tokens for 0 cents, right? So if you've got a token and you don't want to wait for it to mature, you can sell it back to the experimenter for 0 cents. We drop people into one of two conditions. In one condition, the tokens mature according to a uniform distribution. So it's equally likely that they'll mature at 5 seconds, 10 seconds, 15 seconds, 20 seconds, up to 40 seconds. In another condition, it's approximating a heavy-tailed distribution. So it's equally likely the first 20 seconds matches the uniform distribution. And we'll come back to it later when I get to the imaging experiment, why we did that. But if it doesn't come in the first 20 seconds, the token will only mature after 90 seconds. So 50% of the time, the token only matures after 90 seconds. We associate, we've done this between subjects and within subjects. I'm going to show you the data from the within subject experiment. We associate the two times, the two token times, with two different colors of tokens. And we give people experience with two different environments. So they do this task of selling tokens for 10 minutes with green tokens that have a uniform distribution. They do this task for 10 minutes with purple tokens that have a heavy-tailed distribution. And their goal is, within that limited period of time, 10 minutes, make as much money as you can. And so to make as much money as you can, in the uniform condition, what you should do is always wait. So your waiting policy should be to wait up to 40 seconds, up to the last point in time that so to never quit. And if you always wait, you'll make the most money. In the heavy-tailed condition, the best waiting policy would be to wait for 20 seconds. If the token doesn't come in the first 20 seconds, sell it and move on to the next one. That's how you'll make the most money in the heavy-tailed condition. And so our question is, people have, we're going to give people lots of experience with these two distributions. Can they learn to adjust their persistence, adjust their quitting behavior according to the statistics of the environment? In the one case, being maximally persistent, waiting until they get the delayed outcome. In the other case, having a limited persistence, waiting 20 seconds, and then giving up and going on to the next trial if they don't get it in the first 20 seconds. Here's what we see. This is the survival function. This is the probability, given that if the token hasn't paid off, what's the probability that you're still waiting for the delayed token? In the uniform condition and in the heavy-tailed condition, what we see is that these two curves diverge at about 15 seconds, and they just keep diverging after that. In the uniform condition, people are pretty good. 80% of the time, they're waiting all the way out to 40 seconds. So the probability that they're still waiting at 40 seconds is 80%. In the heavy-tailed condition, there's a big drop-off right around 20 seconds, such that the vast majority of people are not waiting when you get out to 40 seconds. So this suggests that if you give people experience with these two different kinds of distributions, one of which where it's sensible to keep waiting and to persist, and the other of which in which it's not sensible to have unlimited persistence, where you should calibrate your persistence and give up after a little bit of time if the delayed outcome hasn't occurred, that people learn based on their experience to do the sensible thing.
Does it make sense to perhaps provide statistics, like even in the survey case, like when you tell them, well, you've been dieting for 15 days, you haven't seen results, would it make sense to say, on average, people after this amount of time would find results? And so that even though they don't have a personal experience, that they've gained this kind of information to make their decisions?
So you can ask the question, how do people combine information that's presented in that way with information that they get from their own experience, with what they bring to the task? Right?
Yeah, perhaps that would, if you know on average that people start seeing results at 20 days, which this kind of information is quite prevalent on the internet, then if you haven't seen results at 15, then you're more likely to wait for that 20, because you're, like, on average, most people start seeing it at 20 or after a month or something like that. Whereas if you don't know these, like especially if you don't have prior experience in dieting, this kind of information would be litmus to you, you probably wouldn't wait. Whereas someone who was to diet would have looked up this information. So, yeah.
So, two answers, one of which is sort of a direct answer to your question, the other is is a little bit of an indirect answer. But just to, so we have we've done the experiment where we've given people explicit information about these distributions and experience, where we where they have both sources. And interestingly, in that situation, the thing that drives their behavior, the thing that seems to drive their behavior is the experience. How do I know that? Well, their behavior is not much different in experience plus explicit compared to just experience, right? So it seems like the explicit, when it's, at least in this paradigm, the explicit information, now the explicit information is not in contrast with the experienced information. So we could ask the question, when the explicit information is in contrast with the experience information, what happens? But at least in that case, the experience seems to dominate. Now, the other sort of more direct answer to your question is I would agree with you that, and I've talked to Angela about this, Angela Duckworth. She's interested in getting kids to study harder and study longer. And I think the lesson from that I would draw from this line of work is that what people's expectations matter. And so if in the dieting case or in the study case, people are coming with not very well formed expectations, if there is some hump at 20 days or whatever, what you would want to do to get them over that hump is to give them the expectation, and hopefully this is a veridical expectation that after 20 days, you're not going to see anything for 20 days, and after 20 days, you'll start to see things, right? That's exactly what you would need to do in order to get people to persist for the 20 days.
Yeah, I'm not sure when to ask this question. I just want to get a sense of how general the analysis is, because there are two other situations that this analysis seems to apply to. What have you thought about that? The first has to do with predictable disasters. That is, disasters we know are going to happen, we just don't know when. People are famously not very good at preparing for them. So the major earthquake that will happen in San Francisco, we know that will happen. Many people are unprepared and not motivated to be prepared. That's one example. The second example is market behavior during boom periods, where people know they're in a housing bubble, but they continue to invest. The problem is everybody knows the bubble is going to burst, they just don't know when. And it takes some very disciplined investors to actually invest into that bursting, because they don't know when it's going to pay off. I was wondering if you thought about those other situations as a more general analysis, other than delay of gratification or.
Yeah. Well, I think the same kind of analysis would apply in the and I've given some thought to more to the market case than to the earthquake case. In the earthquake case, you can imagine that part of what's happening is that I don't know what the actual distribution of earthquake occurrences is, but I would not be surprised if it was heavy-tailed. And if you live in Northern California and there's been a long time since the last earthquake, you might go, well, it's coming, but California's going to fall in the sea after I die, so I don't care about being prepared. In the market case, there's something. There's an additional situation where I think people's expectations are miscalibrated, but so it shares with it a miscalibration about heavy tails, right? Which is, I think people are miscalibrated. So in that case, the actual distribution is heavy tailed, but people are sort of aren't recognizing the tails. They aren't recognizing that there are extreme events that could lead to a market crash, or extreme events that could lead to a huge bull run, a huge run up of the market, and they're sort of following the distribution and assuming that it's normal, and that's not quite the situation that you pointed to, which is people being in bubbles. But I think this is another situation that's sort of well known in the economics community that people seem to not be very bad at, don't seem to take into account extreme events. And part of what I think is happening there is that those extreme event distributions are such that you may never have experience with the extreme event before it occurs.
Actually, this is for a conversation. I differ with you. Often there aren't extreme events. They're just rare events, and it's well within the experience of the market to have known about them.
Okay.
That's another.
Okay. Well, we can talk later. That's. But yeah, I mean, I'm interested in seeing how these ideas might apply. So look forward to the talk later. Okay. So this is the behavior that we see in this paradigm. One thing is we can show this that this behavior is consistent with an estimation of the value of the token that you have in hand. That estimation is this is just your expectation given some wait time that you would get the reward if that's your wait time. This is your expectation of the time at which you would get it given that wait time. This is just a cost of time term. So basically, what's the value of the reward minus what's the cost of waiting for it? And so using this at every point in time, we can crunch through and say, what's the value of the current token that you have in hand? And in the uniform case, that value is increasing as a function of time waited. In the heavy-tailed case, the value of the current token is stable and above 0 for the first 20 seconds, and then drops to 0 at 20 seconds, basically because the best thing you could do at that point in time would be to sell the token for 0 cents. So its maximal value to you is 0. And if we just assume that, so we can get pretty close to people's behavior if we assume that they have some estimate like this estimate of the value of the current token, and that their choices are noisy and probabilistic. And just that assumption about noisy probabilistic choices takes us from this prediction, the dotted line prediction of the ideal model, which is noiseless choice. You should quit right at 20 seconds. However, if choices are noisy, we get something much closer to the actual behavior. So this is just to say that people's behavior, it's not perfectly consistent with the normative behavior in this case, but it's much closer than it might initially appear. We also have some additional data that people develop expectations about the delayed outcomes, specifically in the uniform case, where they're waiting all the way through. And the likelihood that the delayed reward is going to happen, the likelihood that the delayed reward is going to occur is increasing as a function of time. Because in the limit, if you're at 39.5 seconds, there's a 100% chance that the reward is coming at 40 seconds. And what we see with reaction times, first off, reflect that expectation. Reaction times are shorter to just sell the token at 40 seconds than to sell the token in the uniform condition at 10 seconds. And the cardiac response also reflects this expectation. So there's a cardiac deceleration is a signal for motor preparation. And we see that deceleration is more extreme here after a long delay than after a short delay. So both the RT and the cardiac data provide additional evidence that people are, that their behavior is driven by an expectation of when the reward will occur. So the behavioral evidence is that people hold temporal beliefs that make it reasonable to quit delaying gratification before the delayed reward's arrival. That's the survey data. And that in the experimental data, we see that people's waiting behavior is responsive to experience with the temporal statistics of the environment. So if they're put in an environment where it makes sense to wait, they wait. If they're put in an environment where it makes sense to quit after a certain point in time, they quit after a certain point in time. So now let me talk a little bit about the neural data. Yeah?
So it makes sense to me that in a controlled laboratory experiment, you would do it that way. But one way this paradigm differs from some delayed gratification type situations is that there are other forms of uncertainty besides temporal uncertainty, and that includes the value of what the delayed reward is a lot of the time. What's it going to be like? What's it going to taste like? What's it going to feel like? People might do some sort of mental simulation about that, and that's going to affect some of these problems.
So I certainly wouldn't want to claim that the only form of uncertainty that's relevant is temporal uncertainty. I think you could, generalize this viewpoint to take into account other forms of uncertainty. I mean, one form of uncertainty that you could that's easily generalizable from this paradigm would just be uncertainty about whether that reward. We haven't even talked about whether the possibility the reward may never come, right? So that is the reward risky or not? But I think there's in our experiments, we focused in just on the temporal uncertainty, but I think in the real world cases, there may be lots of forms of uncertainty that are leading to that increasing prediction of the increasing prediction as a function of time weighted. The increasing I'm farther away from reaching my goal than when I started, could come from lots of forms of uncertainty in addition to temporal uncertainty. Does that? So I'd grant that. Okay. So our aim with the neuroscience experiment was with the imaging experiment, was to see if there's neural evidence. Our claim is that this behavior in this paradigm is driven by how your expectations about when the reward will occur are changing as you wait. That they're driven by this change in how you evaluate the reward as you're waiting, right? That they're driven by the delayed reward becoming less and less valuable as you wait, because your expectation about the time at which it will occur is getting farther and farther into the future. So can we show using imaging evidence for this reevaluation, for this dynamic, reevaluation over time of the delayed reward, of the awaited reward? So the first thing I need to convince you of before I can answer this question, though, is that there's a neural signal that correlates with someone's evaluation of an awaited reward. And once we have that tool, I think we can go back and ask, what does that signal look like in the case of our paradigm? So is there a neural signal that's a correlate of the value of rewards? We've recently, this is a topic of several of my previous studies, but we've recently done a meta-analysis of over 200 imaging studies looking for positive effects and negative effects of subjective value. So the question is, in these different paradigms, some of them are decision-making paradigms, some of them are just I give you a reward and I measure the brain response. We have some estimate of the value that the subject places on those different rewards or those different outcomes, and they report where's their greater brain activity for the more valuable outcome, or where's their greater brain activity for the less valuable outcome. What's shown here are the brain areas where there's reliably greater activity for the more valuable outcome across 200 studies. And by reliably greater activity, what I mean is there's more effects reported in these areas than you would expect by chance if basically what fMRI is doing is generating random activations across the brain, right? So we can say the brain activations in response to positive effects of value is not random. They're clustered in these areas of the brain. This is what the map looks like for the opposite end of the contrast, so brain regions where there's more activity for the less valuable outcome or item. What you might notice is that some of these brain regions are the same. So there's some brain regions where there's reliable clustering both for positive effects and for negative effects. So how does that make any sense? Well, if you had a U-shaped response, brain regions that responded to intensity or arousal or salience rather than value, it could generate this result if, on the one hand, if in cases where you were looking at rewards as stimuli, these areas that responded in a way that tracked intensity would show more activity for the more valuable item. And if you were looking at cases where all you were presenting were penalties or punishments, these brain regions would show more activity for the less valuable or the lower SV item. And if it was reliable on both ends of the curve, then that could lead to being reliable both for positive effects of value and for negative effects of value. When we do that conjunction of positive effects when in rewards and negative effects in penalties or punishments, it pulls out these regions, the anterior cingulate cortex and the anterior insular cortex being the two most prominent. So this suggests, our interpretation of this is that these are regions that seem to track intensity or salience or arousal. If we ask where is there only positive effects, right? So significant positive effects of value and no negative effects, a true value or valence signal, what we see is ventromedial prefrontal cortex, ventral striatum, and posterior cingulate cortex. For those of you doing imaging, just a plug, we have it publicly available, all the results of this meta-analysis. So one of the reasons for doing this is to sort of move the field away from seeing a brain picture and saying, gosh, that really looks similar to another brain picture that I saw where that was about, the value, or that was about value, or that was about self, and saying, no, here are the regions that are reliably activated by value, and you can use that as an a priori area of interest going forward. That's one way in which we used it in this imaging experiment. Now, in the imaging experiment, basically the same paradigm that I talked about behaviorally, subjects being exposed to a uniform condition or a heavy-tailed condition. And the reason why we had the first 20 seconds be identical in those two conditions was that we were then going to compare brain activity during those responsive to those first 20 seconds. And if we saw differences between those two, we could be confident that any difference in how the brain signal evolved in those two situations was due to the expectations that people were bringing to the situation, rather than the second by second probability that a reward will occur. The second by second probability that a reward will occur, the hazard rate that the reward will occur for the first 20 seconds is identical in those two conditions. If the brain activity is different, it has to be something about the expectations that you're bringing to the situation and how that changes how you're evaluating the awaited reward. So our framework predicts that a condition by time interaction. So I showed you what the value of the awaited reward looks like as a function of time in the two conditions. It's growing as a function of time in the uniform condition. It's flat as a function of time in the heavy-tailed condition. So what we would predict is that in those areas that are responsive to value, that we would see a condition by time interaction, an increase in activity over time in the uniform condition, and activity that's flat as a function of time in the heavy-tailed condition. We find one place in the brain where there's a condition by time interaction. So that statistical analysis, I should say, there's no that analysis could have detected any interaction in any area of the brain. We see one interaction in one area of the brain. The area of the brain where we see the interaction is the ventromedial prefrontal cortex, and the form of the interaction is plotted here. This first 5 seconds or so is, we can show it's in the supplements of the paper, has to do with how we're estimating this this time course. Our estimation procedure just we can't recover the first 5 seconds. We're imparting a decrease in that first 5 seconds based on how we're estimating it. But beyond that, what you see is activity that grows over time in the uniform condition and is flat as a function of time in the heavy tail condition. So it's the only place we see an interaction. It's in an area we would have predicted there would be an interaction, and it's of the form that we would have predicted if this area tracks value. We can also do a model-based analysis where we take our predictions about the value of the weighted reward, we convolve those with the hemodynamic response, and then we ask, where in the brain do we see something that reflects that predicted response, and we pull out the same area, the ventromedial prefrontal cortex. So we take this as neural evidence for a dynamic reevaluation as a function of time, that people's evaluation of the weighted reward is increasing as a function of time in the uniform condition and flat as a function of time in the heavy tail condition. You might be interested in, okay, where does neural activity precede quitting? So now let's take a look at the heavy tail condition and say, what happens as you ramp up to the, forget it, I'm out of here, sell this token and give me the next one. What does brain activity look like? This is the movie of brain activity starting from 12 seconds before a quit event and then building up to the quit event. And then, now you're pressing the button to quit the trial. So, lots of areas are active. I'm not going to stop the movie right before the subjects have hit the button. And two of the regions where you see a buildup of activity before quitting are those two areas that, I don't know why that's not showing up there. It shows up here. Let me just do the full build. Insula and dorsomedial prefrontal cortex, so the insula and the anterior cingulate are the two areas where you see a significant buildup right before quitting. This is the time course in the dorsomedial prefrontal area and that anterior cingulate area, and what you see is that at the 0 time point, which is when the subject quits, but because of the hemodynamic lag is going to be attributable to brain activity before they've ever quit, you see an increase in activity over baseline in the anterior cingulate. You also see an increase in activity over baseline in the anterior insula. Remember, these are the regions that seem to respond to salience or arousal or intensity. If you were to, in the meta-analysis, and these same areas are responding right before the event, leading up to the event where you're going to quit waiting for the awaited reward. And one interpretation we put on this, to the extent that you want to take these areas as reflective of an emotional process or an emotional response, and one thing we're interested in is actually measuring online people's frustration as they do this task. What are their emotions doing dynamically as they do this task? To the extent that you want to take this as an index that perhaps there's some emotional response to waiting without receiving the reward, what we've shown here is that is contingent on your expectations. That in the situation where you have a different set of expectations, you don't see this buildup of the neural response, you don't see this quitting, and it's only in that situation where the expectations are heavy-tailed that you see this response. Now, we've subsequently looked at, so what I've shown you is that the ventromedial prefrontal cortex, that activity there reflects the dynamic reevaluation of the awaited reward, and that signal grows as a function of time as you're waiting in the uniform condition. That evidence doesn't show that signal has any role in people's behavior, right? So it could be epiphenomenal. In order to show that it's functional in people's behavior, what we've done is look at individuals who have damage to the ventromedial prefrontal cortex. And now this is hot off the presses data. we have a group of individuals, 9 individuals, who have damage to the VMPFC. We have a control group of individuals. These are individuals who have damage to lateral prefrontal cortex on either the left or the right. The red here is showing the regions that are damaged in the overlap of the lesions in both groups. And what we would expect based on our imaging data is that if you have damage to VMPFC, you'd be less successful at weighting in the uniform condition if that signal, that reevaluation signal that's growing as a function of time, has some function in keeping you waiting for the delayed reward. And what's interesting here is that there are certainly other frameworks that would predict that in this sort of task where you have to wait for delayed reward, that the key area in facilitating that behavior would be the lateral prefrontal cortex. So we have that. We also have that group in this experiment. What do we see? This is the behavior of the individuals with lesions outside of the VMPFC, mostly in lateral prefrontal cortex. Their persistence in this task is lower than what we see in young, healthy healthy controls. Now, it's also not significantly different from age-match elderly controls. So, and most of these individuals with damage are older adults. And so, I don't know whether the overall decrease in persistence here is due to age or it's due to some difference in this task vis-a-vis other tasks, other versions of the task that we've run. But where did the VMPFC lesions fall out? They fall out with even more trouble in waiting for the delayed reward in the uniform case. So what we see is damage to VMPFC in the uniform case in a high persistence environment where the optimal thing is to wait until you get the delayed reward. We see that people are less able to engage in that strategy when they have damage to ventromedial prefrontal cortex. And then what we've also done very recently is look at individuals with major depressive disorder, depressed individuals. There's some evidence to suggest that depressed individuals have decreased resting activity in ventromedial prefrontal cortex. So in some ways, this might be a much less extreme VMPFC lesion. I don't want to press that connection too much. I present this data mostly out of interest. Valerie mentioned mental health, and I think one area in which we're beginning to get interested in is the extent to which these kinds of paradigms that we've been developing in JDM and in behavioral economics and in decision neuroscience might be useful to diagnose or measure what's going awry in different mental illnesses. And certainly depression is a case where one thing, cognitive therapy is based on changing people's expectations and beliefs. What we see in the depressed group, now this is a case where the control group is much more persistent in the high persistence environment. What we see in the depressed group is a significant decrement of performance. So they're less persistent in the high persistence environment. And give me 1 second and then I'll show you, I'll get to your question. This could be because they're less able to persist in general, or it could be because they're less good at calibrating to the statistics of the environment. They're less good at learning what what to expect in a given environment. The way to do that is to drop them into a low persistence environment. We did this in 2 separate studies. So we had one study with the high persistence environment. This is a study with the low persistence environment. This is what the control performance looks like in the low persistence environment. And what we see is consistent with a miscalibration account as opposed to just a having trouble with persistence account, that they're overly persistent in the low persistent environment. So in the case of depressed individuals, they seem to have a trouble calibrating, learning properly the statistics of the environment. Now, question?
I just wanted to know, just going back to the VMPFC, how is that different from uncertainty in decision making with the paradigm that uses Iowa gambling task?
So, for those who don't know, you're referring to a whole a long literature that's shown that individuals damaged to this area have trouble on a task called the Iowa gambling task. Now, the Iowa gambling task has a lot going on in it. So my interpretation of that, I think that task shows that individuals with lesions to VMPFC have trouble with decision making, and I think it was actually the first demonstration sort of linking this brain area to decision making. It's hard to tease apart using data just from that task what aspects of decision making are impaired, and the reason is just that there's a lot of moving parts. So you come in without any knowledge of outcomes, and you have to choose. You're choosing between 4 decks of cards. You come in without any knowledge of what the statistics are that generate those cards. So there's ambiguity. As you learn, so there's a learning component, and you're learning from experience. And as you learn, you're resolving that ambiguity. But there's still risk. There's also gains and losses, so there's still loss aversion. So there's a lot of, there's a lot of moving parts, and I think it's hard with just that task to tease apart what is impaired and what's not impaired in these individuals.
Yeah, but isn't that literature also like saying that they do not learn, individuals with impaired VMPFC do not learn the good decks from the bad decks. So the reason I bring up the losses and the gains in that particular paradigm is here you're addressing or waiting for a delayed reward as more of a passive, like you're just waiting for something to happen or waiting for someone to pick up your phone. But pretty much when you go back to your first example, it doesn't seem like it's always a passive waiting for something, for the delayed reward. There's always you're working towards it, and sometimes you have gains and you also have losses. So if I want to lose 30 pounds at the end of the month, which is unlikely, but you start saying that I'm going to walk on my treadmill 2 hours a day, and then you get tired next day, you see that you have increased a pound, and then you say, no, I'm going to do it. So I'm trying to think that it's more of that dynamics there rather than just okay, I've decided that I want to lose weight and get that 6-pack. I'm gonna. So that's where I was thinking that it's some sort of a learning also that happens. We take into account even the losses and the gains that we've had throughout the period of waiting. But what you seem to be saying is more attuned to the first paradigm of marshmallow task. Okay, it's just the waiting, and I know that it's either the 2 marshmallow or this 1 marshmallow. So that's
So a lot of things there. Let me before answering your question, just signal that I'm at the end, so we can move on to questions. Here's my summary of what I've shown you, and I can go through the summary. But to answer your question. So first off, just to deal with the Iowa gambling test literature, I think you're right. That shows that these individuals have trouble learning. What they have, and that I think so. There's good data in that paradigm to suggest that where they really have trouble is on the reversal, right? Where the way that task is. Set up is all the gains on the bad decks are right at the beginning, and you don't start getting hit with the big losses until later. And so where they have trouble is in tasks of that form. If you turn it around such that the big losses are early, they don't they don't have trouble. I think that is we can distinguish that discussion from what I think is the motivation for the question, which is that. You're right in saying that all of the work that I've shown you has been, we started with the temporal structure of the marshmallow task, and I think part of what we're trying to do here is pick is to boil down and simplify things and try and find let's deal with one relatively simple situation and get a pretty detailed analysis of it, and then what I hope is that suggests some principles that you could then apply to other situations that differ in the details, right? And you're right that I think the marshmallow task is a case where it's completely passive and you're awaiting the reward, and that's where we've focused our efforts. Our hope is that these principles will be more broadly applicable to other situations like the one I started out with, where you're right that what you would need to add to an analysis of those situations, and one of the things we're very interested in doing is continuous outcomes rather than discrete outcomes. So at each step of the way, you're not just getting no reward or reward, but a gain or a loss towards a goal, and you have to put in work as opposed to just do something passive, right? We aren't done with an analysis of those situations or developing paradigms to look at those situations, but it's something that's on our radar screen. And my hope is that these principles that what people are expecting and what they learn about the statistics of our environment is going to have a big effect on their willingness to continue working or their willingness to continue waiting for a delayed reward will cash out.
We do have time, actually, till 1:10 we have this room, if people want to ask additional questions. I can ask when people up. Sure. To what degree are the results contingent on the fact that there are other rewards in the next trial that are more, you get more if you terminate this trial, you're not going to get a reward, and there's an alternative. Mm-hmm. What if there's no alternative? And you might argue, perhaps, that the Mischel situation is more like that. It's not like, okay, if I don't take this, I'm going to get, you're, in one time it's like that, but then...
Yeah, so, although in the Mischel case, I think there I'd have to go back to at least in some versions of it, it's pretty explicit to the kids that here's a box of toys and we're going to play with it later, right? So, So it's pretty clear. They're pretty clearly signaled that So it's not iterated, but the fact that if I end this, I get to go on to something that's enjoyable.
There's really a time dependency of that. So, the faster I get out of a losing trial and onto the next opportunity, mm-hmm. the more money I may make. That's what I'm saying.
Yeah, so there's a piece that I didn't emphasize that changes as you go from something like the Mischel case to something like our experiment, which is why, where does the cost of time come from? In our experiment, the cost of time comes from the fact that you're only given 10 minutes to earn money. And so the cost of time is, if I'm waiting on this trial, I'm not earning money, right? And if I go into the next trial, I can earn money. That's where the cost of time comes. In the Mischel case, where I think the cost of time comes from is the discounting of delayed rewards, right? So that the fact that you may, now. We could cash it out, right? The fact that people discount delayed rewards may be because of some, cost of time that's not externally imposed by the experimenter. But in that case, where the delay cost is coming from is, I would prefer to have things sooner rather than later. And so at some point in time, in that case, I've got an immediate reward, I've got a delayed reward. When I started waiting, my expectation about when that delayed reward is coming is soon enough that the delayed value of the delayed reward is higher than the immediate reward. As I wait, my expectation about when the delayed reward is coming is now it's farther off into the future, so its value is decremented. Its value is decremented, and so the discounted value is now below the immediate reward, and that's why I quit.
So this all makes sense to me, but then how do you explain this finding that how long the kids waited then predicted how well they did on SATs and other indices of success? Is it that it helps to have this heavy-tailed distributor?
So in that case, to not have it, right? So an anecdote and then my explanation. The anecdote is that, and this is experiments in progress, we find, if you look closely at our data, we find that where people are they're more miscalibrated in the heavy-tailed case in our data, in the experimental paradigm than in the uniform case. And they're more miscalibrated in the heavy-tailed case in that their weight longer than they should. They're overly persistent. And so now we've started online in our paradigm, asking people, how long do you think it's going to be? And we find that expectations are pretty veridical in the uniform case, and they're overly optimistic in the heavy-tailed case. So the anecdote is that I think it may, the experiment we're doing now is, I think that could be telling us something about our subject population, which is Ivy League undergraduates, right? So that's part of my answer to your question, which is, I think this could explain, if this is a generalized propensity to have overly optimistic expectations when in cases where there's delay, that would lead in our world, there are situations where that would be rewarded with better academic performance. There's another way of explaining it, which is that I think where it plays less of a causal role in. So that explanation attributes a causal role to overly optimistic expectations, uniform expectations in a heavy-tailed world. You could have, so the non-causal explanation is just that, and this is more in line with, I think, where Celeste Kidd and Dick Aslan are going with their experiments in the marshmallow task, which is, some kids grow up in a world where older adults aren't reliable and the world isn't reliable, and other kids grow up in a world where older adults are reliable and the world is more reliable and more predictable, and things, so some kids grow up in a heavy-tailed world and some kids grow up in a uniform world, and that's the expectation that they're bringing to the marshmallow experiment, and and that could just be a marker, right, of high versus low SES, for example, predicting later experiments.
And that argument was made years ago.
And
But
yes,
sociology-
we're not the first to suggest that
Well,
explanation.
no, so.
Yeah, we're not. Yeah, no.
But they didn't have brain. Any other questions? Well, you can tell your friends, by the way, that they have not missed this talk, because it will be available free on the Human Development Outreach Extension website, thanks to Chris in the back, our wonderful videographer. So thank you so much.
Thanks, Val.